like to thank Professor Shijen Kwok for inviting me to this nice place. And one more thing, I would like to say my sympathy for the people lost in the ship accident. And so I want to send you. Japanese, all Japanese people are very sad about that accident. Okay. So I have worked on commutative ring theory, and so there are a good point and not good point in commutative ring theory. So yeah, good points. There are many good points, but so the not good point is that so commutative algebra is weak on some classification. And also, so we borrow examples from algebraic geometry. So of course, algebraic geometry is geometry. Geometry is the mathematics which visualize something. And so to visualize something is very important sometimes to get idea. So that is the idea of this talk. Okay. And so I talk about several topics. First, the resolution of singularities. So when I say singularity, so there is some algebraic variety, maybe over some field K. So, sorry. Here. And so this is x and small x. So suppose this is singularity, and so there is a local ring. So the local ring of functions defined near x and which is regular, and so we consider this local ring and write maximal ideal by M. So this maximal ideal is, of course, the functions vanishing at this point. Okay, and so resolution of singularities give some thing instead of x. Of course, definition. So y, yeah. So since I'm interested in this local ring, so sorry. Okay, and so we consider spec of A, and then consider. So this is a resolution of singularity. If first, of course, important, y is smooth, and this f is isomorphism, and the F is projective morphism. And F is isomorphism outside. Singularity of X spec A. Okay. And so first important thing is a concept of rational singularity. So in this case, mainly we work on assume that the field is character 0, and so if the higher cohomology group of structure sheep is vanishing, but so why rational singularity is important for commutative ring theory? So there is a theorem. If we assume Grauer-Riemann-Schneider vanishing. By the way, Riemann-Schneider likes to play flute, and I played many times with him playing piano. Sorry. so Grauer-Riemann-Schneider vanishing theorem is says omega x is just a duality sheaf. Yeah. So under this assumption, of course, this is the holes in character 0 by Kodaira vanishing theorem. So, of course, this is true. So the following are equivalent. First thing is a rational singularity. So this is a definition. And so A is Cohen-Macaulay. Do I need to define Cohen-Macaulay? Yes or yes? So yeah, okay, and yeah, the direct image of omega x is reflexive. So what is Cohen-Macaulay ring? So you can take some f non-zero element f, and then so there is a notion of so f is a non-zero divisor. Of course, if the so non-zero divisor, if this is 0, then originally 0, and so F1 to Fr is a regular sequence. So Fi is a non-zero divisor on F1 to Fi minus 1 for every I. So, okay, so namely, so if we multiply something, Fi to something, and if it is in this ideal, the something is originally in this ideal. So, and so we say depth of A is maximum of the length of regular sequence, and it is known in general always up to dimension of A. And so we say A is Cohomology if depth of A equal dimension. We have equality here. And so let me prove this theorem. So there is a Grothendieck duality. So, yeah, now this is spec A, and this is X, and there is some map F, and Grothendieck duality say F so RF star means some direct image in the category of derived functors. And omega x, omega A, the dualizing complex of A, X, and A respectively. And the important thing is A is Cohomology is equivalent to say so this dualizing complex concentrates in degree minus d omega A. Perhaps it will be difficult, but so I hope you can find the difference, and yeah, and then so by definition this the equivalent. So now put sorry. So for every coherent OX module, now putting F equal OX, and then this condition is equivalent to say A is rational singularity is equivalent to say this direct image is concentrated on degree A, 0, and this is A. Sorry, I forgot to. We assume A is normal and assume so, and since X is smooth, of course smooth varieties are Cohomology, and Cohomology give this thing. So omega x, that dual complex is should also in degree minus t. And then, so now, so if we assume function 1, then so and here, so right hand side, and yeah, so this is when f is ox, this is just omega x, and as I said, omega x d, and assumed 1, this is A, and here we need gravity dimension either vanishing. So higher is 0, and yeah, this is omega A. So this, what this does it mean? So this is first A is Cohomology, and this is f star omega x is just omega A, reflexive. And yeah, we can prove 2 from 1, so yeah, very easy, the same manner. So please try. So for computative algebra, rational singularity is very important because it assures cohomology automatically. And so why I said this in this manner, and so I wanted to say, so the structure of this equivalence. So we want, so especially Cohomology property, and so we reflect what actually we used. So the important thing, most important, is gravity dimensional either vanishing cell. And then we only use Cohomology property of x and not smoothness of x. So of course resolution of singularity is a very difficult question and not solved yet in class P. But for commutative algebra, so I want to say, so we can have something instead of resolution of singularities. And the other thing is, so there are, so we could define a rational singularity in characteristic P by this definition, but it doesn't guarantee cohomology because we don't have gravity dimensionalized vanishing theorem. So that's what I want to say. And what the usefulness of I think this is typical useful. Good to assume A is a subring of ring B is a pure subring. And if B is a rational singularity, so it's A. So what is pure subring? So if A is pure if for every M A module, so tensoring M we have map from M tensor A to M tensor B, and of course M tensor A is we can identify by M, and for every a module this is injective. Yeah, injective is a condition, and so if the condition A is B splits as a module, this condition is strict, implies pureness, and pureness implies for every ideal. So if you lift I to B and intersection, then we have original bar. So, and actually these two are very near condition studied by Hoekstra. So in some sense nearly equal. So, and important corollary of this is so HG and linear algebraic group acting linearly linearly reductive. Linearly on the polynomial ring. So we assume that G is a subgroup of GLN, linear group of n variables. Then the invariant subring is Cohomology. Of course, this comes from SG is a pure subring of A, and so this is a rational singularity, and then Cohen-Macaulay. Okay. And so how to recognize some singularity is rational or not? So this is was our first very big problem for me, and in this manner. And assume that A is R. So consider graded ring. So graded ring is ring is divided into homogeneous parts, and Rm times Rn is included in Rm plus n. So, and so normal Noetherian graded ring. Then R is a Cohen-Macaulay, rational singularity. If and only if there are three conditions. R is Cohen-Macaulay. Sorry, I forgot to say that degree 0 is a field of character 0. And so then we write R plus for positive part of R, and of course this is maximal idea, since this is the field, the degree 0 is, and spec R is so outside closed point rational singularity, and then the most important thing is negative A invariant. So the notion of A invariant was introduced by Goto and myself. So if R is a graded ring of a dimension D, then AR is the maximum of HD. So this is local cohomology with respect to M. N. Sorry. Maximum N such that HD degree N part of is not 0. Sorry for introducing notion of local cohomology, and so but in many cases it is easy to compute. For example, so if R is So polynomial ring, but so we put and degree xi is ai, degree of fj is bj. Then, and if f is 1 to fr makes a regular sequence, and in this case, this R is called a complete intersection. Then, in this case, AR is just the sum of BJ minus sum of AI. Okay. So, for example, consider hypersurface xyz modulo xa plus b to the b to j to the c. And so this should be homogeneous in some sense. So to make this homogeneous, the easiest way is put degree BC here, AC here, AB here. So then, so this equation will be homogeneous of degree ABC. So A invariant is of R is just ABC minus BC minus AC minus AB. And we can write ABC times 1 minus 1 over A minus 1 over B minus 1 over C. And so for R to be a rational singularity, the important condition is negative A invariant. And negative A invariant is just equivalent to say 1 over A plus 1 over B plus 1 over C is more than 1. Okay, so I'll come to this example again in few minutes. Also. And so this is the first section about rational singularity. So I'm sorry to yeah. And so my first big problem was about rational singularities. So of course we defined the notion of A invariant so that we get this theorem. But so and so
the AR is the maximum N, H, N, B, R, N is part zero. So maximum can be negative also. Yeah? And N can be negative.
Sorry, I can't hear.
Definition of AR.
Yes.
There's maximum number of N.
Yeah, yes.
So N
I see. So this local cohomology module is graded module which is Artinian. So submodules are decreasing. So it should be 0 at some place. Is that your question?
So here n can be negative number or n.
Yeah. So this means the n degree n part of this local cohomology module. Okay. So this has a structure of graded module of R.
So that depends on the grading.
Yes, of course.
So then maybe small n may be negative if we have different grading.
Yeah, yes. Okay. Thank you. Okay. So what I want to say is to analyze singularity of class 0 by method of commutative ring theory of positive characteristics. So the main tool is the tight closure theory of Hox and Huneck. So what is this? So let A be a ring of Noetherian ring containing some field of characteristic P positive, and then in this case if you take P's power of A plus B, this is just A to the P plus B to the P. And hence, we define A, so if small a is A to the P, this is a ring homomorphism. And this is called Frobenius map. And so, when in the part of rational singularity, I talked about gravity-dimensional vanishing. And gravity-dimensional vanishing is proved by Kodaira vanishing. And Kodaira vanishing, so the proof of Kodaira vanishing needed functional analysis, some analysis. And so, when I was a student, my advisor said, so algebraic geometry very difficult important theorem uses analysis. But so my motivation is so replace algebra at that point. So and yeah, so I think until a certain point we are successful. So and okay, so for some ideal A, and we use the letter Q some power of P, and then I to the bracket Q means the ideal generated by Q's power of elements of I. Okay, so we define I, the tight closure of I, ideal I. For simplicity, we assume A is the integral domain. No zero divisor. So yeah, X is in, yeah, of course X is in A. X is in tight closure of I if and only if exists C non-zero element for every Q C to the X is Q, C times X the Q is contained in as the bracket Q. Of course, if X is originally in I, of course this is holds. So of course then I star is bigger than I, and this actually this is an idea called tight closure of I. And so by this, and I is called tightly closed if I star is just equal to I. So, and we call A as weakly F regular F regular means near to the regularing and yeah, from the viewpoint of Frobenius map. So we could F regular if I is for every ideal is tightly closed. And then locally A is F rational if for every parameter ideal, parameter ideal is just ideal generated by D elements, D's dimension. So, and then primary ideal. And for every parameter ideal is tightly closed. So of course, this condition restricts ideal and certainly weaker than 3. Okay. So the most important thing is so let me come back to equal x to the a to y to the b to the c. So maybe localize as a maximal ideal. And then take I, sorry, change from this to B because we have C there. And so let's put I, Y, Z, the image of Y and Z, X, Y. So the problem is when I is tightly closed. So I want to show you sometimes tight closure is easy to compute. Sometimes. And so take Q equal P to the F. So this is high power of, and then so if we compute R modulo I, so you divide X and Y, so this is KZ over Z to the E. And then, so the smallest ideal strictly containing I necessarily contains Z to the E minus 1. So I equal I star, I equal tightly closed if and only if Z to the E minus 1 is not contained in tight closure. So let's compute. So what was the condition here? Condition is there. So first, element Q times, and we write Q over E equal S times N, E, this is E. Q times E minus E, equal E times S plus R, and R is just divide by E, and then you know that S is near to the E 1 minus 1 over E to the Q, and so then C to the E minus E 1 times Q equal plus minus XA plus Y to the B times S times Z to the R. Okay, This is just a complication. Sorry. Okay. And so the condition is C times should not be in I to the bracket Q. So if you expand this part, so the condition is every term should not be in here. And so in expansion, every term has power less than Q. So the condition is AS plus BS should be larger than twice. If this is rather more than twice, so some element has Q's power, then so the S is included in IC bracket Q. So then now easy to show that it's not in So C time S equal Q times 1 minus E. And this one over A plus 1 over B plus 1 over E is larger than 1. And so we saw the same condition here. Actually, so this is if P is larger than 5. If P is at most 5, then the compass holds. Star is strictly bigger than I. And so this theorem sorry. So if A is so essentially of finite type, over K of set to 0. So then there is some B essentially of finite type. Sorry. Okay. Over some R. R is of finite type over Z. Finite generated over Z. And A is B tensor obtained as K. So we consider this. So then since R is of finite type over Z, so if take maximum ideal of P, then M times B has positive characteristic. P. And then, so P tends, sorry, R, sorry, this is R. We call B tends R over M reduction mod P of A. And so we can discuss if this is F rational or F regular. And here we say that A, the reduction model of P of A. So theorem. So Karen Smith and Nobuhara and Meta Srinivas. So A occurring in case 0 is F rational singularity if and only if the reduction model of P of A is F rational for every large enough P, like that case. And so we have some kind of dictionary. So, of course, rational singularity is translated to F rational equals P, and the notion of log terminal singularity is translated F regular. So, log terminal singularity assumes equivalence time. And log canonical singularity is supposed to correspond to F pure singularity. F pure means this is a pure map. Pure, I defined pure. But actually, so this part is proved, but the other part is still open. And so there is notion of multiplier ideal. And this is, so I can say the definition. So test ideal in characteristic P This is due to Hara and Yoshida. So when is this dictionary complete? Sorry, so my time is over. And I plan to talk about some more topics, but so Professor Kwok has some resume of this talk and proceeding. And so perhaps interested people ask him to, for the, yeah. Thank you very much.